So yesterday we took a look at the levels of organization, and we specifically looked at interactions that happen at the community level. But today we're actually going to take a step back and look at populations. So a group of the same species living in that same place. And specifically, we're going to look at how they grow, and we're going to look at something called limiting factors, which are the things that stop their growth. So we're just going to take a look at how populations grow. And most populations, all populations really grow in a way that we call exponentially, or at least they appear to grow exponentially. So remember that a population is a group of individuals that belong to the same species living in the same area. So, for example, this is a population of ducks because they're all the same species of duck. They're mallard ducks. They're living in the pond. So a group of individuals that belong to the same species live the same area. Here is a population of deer. Because they're deer and they're living in the field. So we say that these populations will grow exponentially. And what that means is that the larger the population gets, the faster it's going to grow. So if you think about maybe some deer, right? And you think about maybe Papa deer and Mama deer. And you think about, year one, Papa and Mama meet and they have a couple kids. So next year, your population might be 4. And that population might have a mix of males and females within it. So some of those males and females in year 2 are going to be breeding. And so for each parent, you might have 2 more children. So these 2 parents might make 2 more kids, and these 2 parents might make 4 kids. And in year 3, you might end up with, say 6 kids. And then let's say from there, these 2 parents have kids, and these 2 parents have kids. And now you're looking at 8 kids, and then so forth and so on. Every set of children that are born become parents to the next generation. And because you're doing that, there's more babies being born every year. Basically, you can think about it this way. The babies are growing up to make more babies before the adults die. The same thing happens sort of with humans. If me and my wife were to have 4 kids, well, each of those 4 kids is going to marry and could make 4 kids of their own. And all of those kids could marry and make 4 kids of their own, and so forth and so on. So it keeps growing and growing and growing. And the larger it gets, the faster it's growing. And if you were to graph this, it's going to create the following shape. You're going to start off with a small population of maybe 2, but quickly as that population gets bigger, there's going to be more and more parents to make more and more babies, and it's going to skyrocket up. This is called a J-shaped curve, or it's called exponential growth, or an exponential growth model. And it always kind of takes this shape. It starts off slow, and then it kind of skyrockets up. One species that does this very well are bacteria, say in a petri dish. You might, leave your petri dish and out, and then the next day it's just covered in bacteria, because one bacteria make 2, those 2 make 2 more, which is 4, those 4 make 2 more, which is 8, so forth and so on. So it just grows very rapidly. Now, if you think about this exponential growth, it would just keep happening and keep happening and keep happening. But that doesn't really work because they're going to be limited. Any population's growth is limited by certain factors. You can think about it like this. Ecosystems can only hold so many organisms. We call these limiting factors. Think about it like a bucket, water. I can turn this faucet on, fill up my bucket, but eventually the water will keep pouring into the bucket and then pouring off the side. The bucket can only hold so much. Ecosystems can only hold so much. The environment that these populations live in, whether it's a pond, a forest, can only hold so much. And if you think about what might limit that population, well, the obvious one is resources like food. If there's only so many acorns in the forest, only so many squirrels can live. So although they'll grow exponentially, eventually they're going to run out of food. Another one is just predation, right? If there are more organisms to hunt, it'll be easier to hunt them. If there are more cattle out in the prairies, the lions are going to have an easier time catching them, which means there's going to be fewer and fewer cattle because there's so many around. It's easy to just grab them. Space is a big one. There's only so much space in any given ecosystem for organisms to live before they're just too crowded. We see this actually happening with humans in China. You can see this picture. It's insane. There's only so much physical space for that population to exist. Diseases become more common as populations increase. You can think about this, why are colds more common in the winter? They always say it's because, well, in the winter, everyone goes inside, everyone's closer together, and it's easier for those germs to spread. As a population gets bigger, it's easier for diseases to spread, and those diseases can stop your population from growing. And then just things like natural disasters that occur, weather, climate interactions, floods, all those things kind of keep populations from growing because if you have a large population, a big disaster hits like this fire, it's going to kill all the trees, and you're going to start from scratch. So that population can only get so big before another forest fire will occur. The bigger this population of trees is, the more likely that fire is to spread. So bigger population may make it more likely that things like this happen. So when we include all these limiting factors into kind of our exponential growth model, it changes the graph somehow. And the way it does this is it creates what we call a carrying capacity. All carrying capacity is that factor that limits a population growth. So whatever that one factor is, and it's always going to be the least smallest factor. So usually it's food. There's only so much food for these organisms to eat. Once we hit that factor, it's going to stop our population from growing. So we call that limit the carrying capacity. If we were in a forest, well, maybe this forest only has enough food for 30,000 deer. So the deer can grow exponentially, and babies are making babies and making babies. It really can't go above this line. That's our limit because we're going to run out of food. That's our carrying capacity. So what it does is it changes the shape of our graph. We say that the population grows exponentially until it reaches its carrying capacity. So a graph might look something like this. Over time, here's your population. It's growing really quickly, but then as we get closer and closer to that carrying capacity, that limit, we start to slow down until we kind of plateau there. That's the biggest our population can get because we run out of food or resources or anything. And this graph isn't 100% accurate to what you might see in the wild. A lot of times what populations do is they accidentally overshoot their carrying capacity. So the species will make more children than the ecosystem can support. So this line will actually go above the carrying capacity. And then by the time that kind of everyone realizes that we're out of food, it's a little too late and it dips back down. And lots of organisms need to die before it can sort of level out. But that's just the way it works. So this whole type of growth, one that grows exponentially but then slows down, we call it logistic growth. And so almost all populations actually grow logistically. They grow with this S-shaped curve because they reach. And you can see the two here, exponentially, which is unrestricted growth, versus logistic, which is restricted growth. Here's a population that would grow forever and ever and ever. Here's most populations that kind of hit that slowdown. They hit that line and have to kind of taper off their growth because they're running out of food or water or resources. One interesting thing that you're going to take a look at is the growth of human populations, because as far as humans grow, we've been growing exponentially for the past few hundred years. Actually, the number of humans on planet Earth has been growing exponentially. And one of the issues that we foresee is that Earth itself has a carrying capacity of humans, and there's only so much food, space, or water for humans to live on this planet. And a lot of scientists believe that humans have already gone past their carrying capacity, that there are too many people on the planet, and we're going to start running out of food or water or resources. And again, if you go above your carrying capacity, you dip back down. People have to die before you level out. So we're really worried about this kind of whole idea that we've gone past our carrying capacity, that we don't have the resources to support all the people on the planet.